Today, we're taking on a problem that seems simple on the surface, but offers a great lesson in array optimization: decompressing a run-length encoded list. How can we efficiently reconstruct the original data without unnecessary overhead? Given a list of numbers representing a run-length encoded list, we need to decompress it. The input array consists of pairs, frequency followed by value. For instance, if you see 1, 2, it means the number 2 appears once. If you see 3, 4, it means the number 4 appears 3 times. Your task is to return the decompressed list as a single array. A straightforward approach involves iterating through the input array, taking each frequency value pair. For each pair, we simply add the value to a dynamic list, like a C# list, as many times as its frequency dictates. While this works, repeatedly adding elements to a dynamic list can incur performance penalties due to frequent reallocations and memory copying if the list's underlying array needs to grow. This brute force solution has a time complexity of big O of n and space complexity of big O of n, where n is the total number of elements in the decompressed list. The key insight for optimization here is that we can determine the exact size of the final decompressed array before we even start filling it. Instead of using a dynamic list that might resize multiple times, we can pre-calculate the total length. First, iterate through the input array, summing up all the frequencies. This sum gives us the precise size needed for our result array. Once we have this total length, we can declare a fixed size array of that exact dimension. Then, in a second pass, we iterate through the input again. For each frequency value pair, we fill our pre-allocated result array directly at the correct indices, incrementing a pointer as we go. This avoids all the overhead of dynamic list reallocations, leading to a more efficient memory usage pattern. Let's trace this with an example. Input array 1, 2, 3, 4. First, we calculate the total length. The first pair is 1, 2, so frequency is 1. The second pair is 3, 4, so frequency is 3. Total length is 1 plus 3, which equals 4. Now we allocate a result array of size 4. We then initialize an index to 0. Back to the input. For 1, 2, we add 2 to our result array at index 0, then increment index to 1. Next pair, 3, 4. We add 4 to the result array 3 times at indices 1, 2, and 3. Each time, we increment our index. So 2 goes at index 1, index becomes 2. 4 goes at index 2, index becomes 3. 4 goes at index 3, index becomes 4. Our loop finishes. The final result array is 2, 4, 4, 4. This is correct because we had 1, 2, followed by 3 4s, exactly as specified by the run-length encoding. You'll spot this pattern whenever you need to build an array or list, and the final size can be determined by a preliminary pass over the input. This is especially true with problems involving fixed-size transformations or aggregations, where dynamic resizing is a known performance bottleneck. The optimal solution has a time complexity of big O of n due to 2 passes, and a space complexity of big O of n for the output array. This pre-allocation trick is fundamental. Try applying it to other array construction problems. If you found this helpful, hit that like button and subscribe for more DSA insights.